It's my pleasure to introduce the next speaker of today's sessions. It is David Patterson, recipient of the ACM AM Turing Award in 2017. It's fairly recent. For, and I quote, pioneering a systematic quantitative approach to the design and evaluation of computer architectures with enduring impact on the microprocessor industry. He will talk about the impact of AI on processor architecture, or put it more precisely, on the special requirements included by AI technology on what processors should provide in terms of functionality. There will be time for questions, and the audience is encouraged to send questions via the chat channel of the HLF app, and we will then relay these questions to David after the presentation. The presentation itself is pre-recorded. If there are more questions than can be handled in the remaining time frame, then of course we have to stop at some point, but nevertheless you are encouraged to ask questions via that function. With that said, we can start the recording. David.
Hello, I'm happy to talk to you about how the importance of computer architecture affects the rate we're going to improve artificial intelligence. Artificial intelligence started in the 1950s, and the dominant way to think about it was a top-down approach. If we just wrote down all the rules, kind of if this happens, do that, and got the rule set right, with the proper logic, intelligence would emerge. But within artificial intelligence, there was another group that said that's impossible. The only way we're going to learn that is from the data. You have to go bottom up from the data to create those rules. Human beings can't figure that out themselves. And within machine learning, there's another group that said the only way we can do this is supervised learning, where we try and imitate the neurons of the brain. And this is called deep neural networks. Deep neural networks have two pieces: training, where you're deriving from the data a model, and then once you have that model, you infer it or serve it. You put it to work. So training could take days, but inference could take milliseconds. And this deep neural network piece is what led to the Turing Award to Hinton, Bengio, and LeCun, who got it the year after Hennessy and I got it, and recognizing the contributions. So what we see as advances in AI is really advances in deep neural networking starting to work. So why is it starting to work? These aren't new algorithms that they invented. The algorithms have been around about 20 years. What's happened is that we needed a lot more data and a lot faster machines than when those algorithms were invented. It's easy to get more data today from the cloud and Internet of Things devices, but what about faster machines? Sadly, just as we need much faster machines, Moore's law is letting us down because Moore's law is getting to slow down. And as you can see in the graph below, this is Moore's law prediction of doubling every 2 years, and versus microprocessors that came from Intel, in terms of the transistors per chip, we're off at least a factor of 15 where we would be if Moore's law still held. And that lack of transistors per chip turns into performance, as you can see the graph on the right. In the 1980s and 90s, when Moore's law was alive and well, we were turning those transistors into faster computers, so doubling performance about every 18 months. At the time, people would throw away perfectly good working computers because they were 2 years old and much slower than your friend's computer. These days, nobody gets rid of a good computer. If my laptop, I throw it away only if the battery breaks or the display breaks or something like that, because the performance is about the same. And indeed, in benchmark measurements, it's only improving a few percent per year. So instead of doubling performance every 18 months, we double performance every 20 years. So we need faster machines. How are we going to do that without the help of Moore's law? Computer architects think the only way we can do this is domain-specific architectures, DSAs. They don't try to do everything, but just do a few things exceptionally well. What this means for computer architects is 5 decades of experience of designing general-purpose processors may not apply. So if you're a researcher, this is an exciting new times, new innovation, brand new ways to design computers. Oh boy. But however, if you're at a company trying to sell products, it's a very scary time because which thing should you build? And we need these domain-specific architectures for both the cloud and the edge. So the cloud is simply warehouse scaled computers with 50,000 servers in them at remote places. They also have storage in them and distributed data centers around the world that are connected via the internet. That is the cloud. Warehouse computers all over the world. And the edge is the tiny computers, the often battery powered, Internet of Things, or cell phones or laptops, cars, tennis shoes, everywhere. So that's the cloud and the edge. Let's do them in sequence, starting with the cloud. Well, Google was one of the first people to get excited about both deep neural networks and then domain-specific architectures. In 2013, they calculated that if 100 million users started doing deep neural networks 3 minutes a day on CPUs, they would have to double the size of the data center. Not only would that be very expensive, it would take forever to build twice as many data centers in the cloud. So they set an emergency project whose goal was to make a factor of 10 improvement over existing CPUs and DPUs. And they gave them very little time because this could happen any day that people want to start using deep neural networks. So that it was done in just 15 months from ideas to working hardware and software. And they exceeded the expectations, remarkably enough, in that short time. It was about a factor of 80 times better than the contemporary general purpose CPUs and about 30 times faster than the NVIDIA GPUs. And putting this in perspective, these are amazing numbers because factors of 10 in commercial products are rare. You can sell a lot of products if you're only a factor of 2 better. This was factors of 10 to 80. Why? Why was it so successful? First of all, an amazing number of arithmetic units. It has 256 by 256 arithmetic units, 64,000 multiply accumulators. Secondly, that they were doing work on 8-bit integer data rather than 32-bit floating data, so it can be more energy efficient and take less memory capacity and be faster. And because it was domain specific, it dropped a lot of the general purpose features that dominate CPUs and GPUs, like caches and branch predictors. This saves area and energy and lets the transistors get reused for domain-specific hardware. Okay, TPU v1 was success. TPU v1 was for inference, which is the simpler task. So for TPU v2, they wanted to take on training. So it's a bigger task because it's more computation, it needs more memory, and the data has to be bigger than 8-bit integers. And then trying to figure out what were the good ideas that we should carry over and what had to be new. Well, first thing was, I said, it takes longer to train. It could take on Google's production applications, if we were trying to do it with one chip, it could take more than a year. So that's obviously, no one's going to wait more than a year to get their results back. So when you think about the bigger machines and more data lead to bigger breakthroughs in machine learning, that was true in 2015, just like it is today. The goal was to build a supercomputer for deep neural networks. And in retrospect, that was a great decision. Here's a result from our colleagues at OpenAI, just showing the thirst for machine learning training. So if you wanted to stay at the state of the art, they calculated going back to 2012 up through 2019, the appetite is 10x per year. Whereas Moore's law, which, when it was at full speed, was 10x every 5 years. So dramatically faster appetite for training at the very state of the art. A critical feature for a supercomputer is how the chips talk to each other. Google decided to build inside every chip what we call ICI or intercore interconnect. Each link in each direction has 500 gigabits per second, and there's 4 of them per chip, so that's pretty phenomenal. But it's not very expensive. It uses only 1/8 of the die to do the distributed switch and the interconnect. And the TPU v2 supercomputer scales up to 256 TPU v2 chips. So compared to the classic data center network, the links are faster. It's cheaper because there's no network interface card, or there's no switches in it. So it's cheaper, faster, and those don't form bottlenecks. And so that maybe it's 5 times faster at 1/10 the cost. So this was a big feature for our domain-specific architecture. Then the question is, designing chip, how many cores per chip? For TPU v1, we had 1 core per chip. But GPUs can have 100 cores per chip. So where should we go? Well, the challenge is as the feature size gets smaller with more advanced semiconductor technology, the global wires that go across the chip don't scale anymore, so the delay increases. So that's an argument for not making too big a core chip. Now we know that training can lose lots of processors, so it's accepted to use more cores. So where we went to advice is Seymour Cray, the greatest supercomputer architect of all time. And when he was asked the way he said how many cores, he said, if you're plowing a field, what would you rather use, 2 strong oxen or 1,024 chickens? So we went with 2 strong oxen. So the TPU v2 has 2 cores per chip to prevent the longer, so it wouldn't have a slower clock cycle. And we thought it wouldn't be much easier to do 2 beefier cores per chip rather than 1,024 wimpy cores. What about the supercomputer arithmetic? The TPV1 success was this 256 by 256 8-bit integer multiply and accumulate. If we did that for 32-bit floating point, that would just be too much area and too much energy to do that on a single chip. And 16-bit floating point is much faster. Typically, it would be 8 times faster because the mantissa that you multiply is much smaller. So we experimented with doing floating point using 16-bit floating point. Now, if you can see in the format below, the IEEE standard, which was developed by Berkeley and led to my colleague Bevil Khan winning the Turing Award, 16-bit IEEE floating point has only 5 bits of exponent. So that is a very narrow range. You need to represent really small numbers when you're dealing with training on CPUs, and 5 bits of exponent doesn't support that small a number. So what they found was, if they tried to do an IEEE floating point, they ran into problems. But if they kept the exponent the same as the full precision, which is 8 bits, they didn't. But they didn't need very many bits of transition. So this brain float format has the same exponent, 8 bits, as single precision, but only 7 bits instead of 23 bits single precision, and that worked just fine. So this is a great result because it's faster, it's less die area, because the multiplier dominates. The multiplier at 7 bits is half of the die area of a 10-bit multiplier. And it's also half the energy. So it works better for software, less hardware, less energy. So BrainFloat is a much better match to machine learning training. And in fact, as a result, everyone else has embraced it. ARM, Intel, and many startups have decided to include BrainFloat for machine learning. This is the floor plan of what the chip looks like. The dividing line in the middle shows the 2 cores, upper core and a lower core. The matrix multiply units, only 10% of the chip, interestingly. And as I said, the ICI links there in purple are just about 12% of the chip. Google did a second implementation of the same technology. After doing it, they thought that with a little bit more work, they could do another one that would be even better. So the TPU v3 has about 1/3 faster clock. The ICI interconnect link bandwidth is about 1/3 faster, and the memory bandwidth is about 1/3 faster. The big change is they decided they can do 2 of these multiply units per core rather than 1 per core as in GPV1. So 1/3 faster clock and twice as many cores, it's about 2.7 times peak performance. Now, to go that much faster, they burned a lot more power, And so it went from an air-cooled design that was on the prior slide. And so in the middle of the slide, you see these gray pipes connecting the 4 TPUs together, and those pipes contain liquid that cools the chips. It has more memory, twice as much memory as TPU v2, and we can scale up to a much bigger supercomputer. It goes up to 1,024 chips. The die size grew only a little bit. It was in the same technology despite these enhancements, because basically the Google designers had a better idea of how to do the layout the second time around. Before we talk about scaling, let's talk about individual chip performance. Well, we need to do benchmarks. Now for TPU v1, we use production applications to evaluate that, but that works for Google, but no one else could use Google's production applications because we keep them secrets. And so we helped create benchmarks that the whole industry use called MLPerf. We, with some other organizations, got it on the ground floor. So we've got 2 sets of evaluations of how the speed up of the TPU v3 is over the contemporary GPU, which was the Volta. So using the MLPerf benchmarks, where Google works hard to get them running and NVIDIA works hard to get them running, it was about a tie. It's about the same speed. The geometric mean is 1. Now, if we look at Google production applications, it's completely different. The TPU is 5 times faster. So how could that be? Well, what the problem was when we talked about that brain floating point format, the B float, which is in TPUs, was easy for Google application developers to use, but they couldn't and didn't want to get IEEE FP16 to work because that takes extra work to get the same results, and you have to change the software to do that. So we didn't do that. So we thought, so that was our experience, but we're not the only one who does that. The Vector Institute also is in Toronto. Only one of the 200 people used the 16-bit floating point when they use GPUs. Everybody else uses 30 points. So we'd probably get that same factors of 5 results, different there. Okay, let's talk about scale up. Remarkably, AlphaZero, this is the program that beat all human beings of the world at both chess and Go and one other game. It is almost perfectly scaled up. So with 1,024 TPU v3 chips, it goes 980 times faster, which is 96% of perfect speed up. And 3 other applications run at 99%. So it's just almost perfect scale up. It's just what you want from a supercomputer. How can we compare this domain-specific supercomputer to conventional supercomputers? Well, it's not going to be apples and oranges, but there's some similarity. So we're going to use the AlphaZero program, that one that beats everybody at chess. This is the production program in Go, and using it real data. And it's using BrainFloat 16 and IEEE 32-bit. That's its calculations. For supercomputers, the most common benchmark is Linpack. This is a benchmark that isn't fantastic. You can scale up to any size in Linpack to keep all the processors busy. This is called weak scaling, and it's synthetic data. It's not real data that is created. So the more chips you have, the more data you get. The other difference, they're not running the same benchmark, and also this is doing 32-bit and 64-bit floating point instead of 16 and 32. And so the results are at the bottom. So remarkably, running a production application, AlphaZero gets 70% of peaks. That's 70% of 1,024 chips times the peak performance per chip, which is amazing. But you can see for Linpack, the 2 supercomputers we have here get about 60%. In terms of the actual petaflops per second, it's almost 90 for TPU v3 versus 60 and 1. The reason this slower computer there in yellow is there is because there's another way you can look at the Linpack results. It's called the green 500, which resorts the top 500 lists by flops per watt. And the green 500 winner is the Saturn V there at 15 watts. But TPU v3 is 10 times better performance per watt than the #1 green supercomputer, which is pretty remarkable. Let me conclude. Moore's law is slowing down just at the wrong time. We're going to have to tailor our machines to AI for both the cloud and the edge, for machine learning training and inference, because the transistors are not getting that much better. Fortunately, from a computer designer's perspective, the machine learning appetite is ravenous. For example, GPT-3, which was recently in the news, makes pretty impressive imitation in terms of writing in human language. And what's the big idea? The big idea of GPT-3 is simply bigger. It has 100 times as many parameters as GPT-2. They had calculated on their own that a factor of 100 should dramatically improve the quality, and it did. From a computer design perspective, by being domain specific, that really simplifies supercomputer design. How much performance we need per node, what type of arithmetic you need to do, how much memory do you need, the speed of the network links, the topology are simpler when you're trying to do a specific domain rather than doing everything, in this case, machine learning training. Google's TPU supercomputer demonstrates factors of 50 improvement in performance per watt over general purpose supercomputers, which is an amazing benefit. I think this decade is going to go down as a Cambrian era of computer architecture. We'll see many exotic species appear to try and do this tailoring, and we'll learn later which ones will flourish. As you can see, I've magically transported myself here to Heidelberg, and I'm ready to answer questions.
Session. Thank you very much for this great presentation, for this overview. We are still checking the chat channel to see which questions came in from the audience. Just checking the technical parameters at the moment. All the the right microphones are on and the other ones are off, and so on. I'm receiving the first questions, and I'm reading them just as they appear. First one: irrespective of the amount of training time, can hardware type, for example, CPU, GPU, TPU, cause variation in the learning quality of the deep learning model?
Can different hardware cause variation in the learning? I mean, you're trying not to do that. What you're hoping to get it be portable across all the applications. If you're writing this in PyTorch and TensorFlow, you don't really want to have to retrain things if it's running on different hardware. So our goal, just like porting any other program, is to be compatible and get the same answers across all the platforms. So hopefully the answer is no.
Okay. Second question is the high bandwidth memory considered the go-to domain-specific memory for machine learning? How does the machine learning thirst influence the current DRAM technologies?
Great question. It appears that a lot of this computation is memory intensive, and so the speed of the memory affects how fast you can do things. Especially, as I mentioned towards the end, this interest in giant models. The two types of memory are static RAM that fits on the chip and dynamic RAM, where you can buy them in lots of chips. The high bandwidth memory is for the dynamic RAM. As we're getting these really big models, it's just not possible to keep them all in the static RAM on the chip. So the speed of access for that DRAM is very important. Another issue in terms of memory technology is actually the cost. And if we're going to start doing models that have hundreds of billions of parameters, we may have to start looking at more exotic memory technologies that are cheaper to hold all the devices.
Okay, thank you. The next question is a fairly long one. I'll start reading it. Thanks for the nice talk. On slide 14 and some after that, you mentioned the use of half-precision floating point format. So is the sacrifice of precision for performance? The question is the precision important in AI world? Besides, how about the use of POSIT instead of the IEEE floating point number?
Yeah, in general, I think if you talk to people in machine learning, they say precision isn't as important as it is in scientific computing and high performance computing. So because precision is so important in high performance computing, they almost always use double precision floating point for their calculations, 64-bit floating point. What we found, and what many people have said, we don't need that for machine learning. It's a stochastic process. So what we found is that 16-bit floating point seems to work well enough. Now, the IEEE standard, for which, as I mentioned, Professor Kahan on the standard, the 16-bit version of them has the wrong balance of exponent and mantissa. For machine learning, you want to have a bigger range with these small numbers. By using small numbers, they're much more energy efficient and more memory efficient, but you need a bigger exponent than IEEE standard. Posits is an interesting research area. That's still to be determined how important that'll be. We can certainly do really well with what I mentioned, this other format called BrainFloat, and it's become a standard data type. All companies have implemented it. So I don't see floating point formats as an obstacle to making progress.
Short question from my side. Did you talk to William Kahn about BrainFlow? What does he think about it?
Yeah. Right now in COVID, I don't get to talk to anybody. I did ask about posits, and he is not a fan of posits.
Okay.
But I haven't had a chance to talk to him and see what he thinks of BrainFlow. I'm sure it would be a very long conversation.
I'm sure, yeah. Okay, next question. What do you think about using memristos for realizing neural networks? In recent years, there have been an emergence of research on memristos that bring memory and computing close together. What do you think about deviating from von Neumann's architecture this way?
Yeah, I think this, in general, there's this area called processor and memory. I worked on this earlier in my career. We had a project called Intelligent RAM. I think it'll be interesting to see if there's areas of or there's pieces of the machine learning problem where this is a good application. Memristor is a more novel memory technology, and I think maybe there'll be some embedded applications where the non-volatility, so it's like flash, if you turn it off, it doesn't forget it, of the memristor is going to be an interesting application. Basically, what's happened in computer architecture is a lot of ideas that didn't work for general purpose computing have been resuscitated and being evaluated for machine learning for this domain-specific architecture. Just practically every idea we ever tried is being retried here. So I think processing new memory, using more novel memory technologies will be, it's part of what I call this Cambrian age. We'll see all these investigations. It's hard for me right now to see that that's going to be a winner, but it's a good time for doing these investigations.
Next question. If you increase the number of parameters for a learning model for better performance, the need for computer increases. However, is it really hardware that needs to catch up, or is it that current algorithms are yet to fully utilize current hardware capabilities?
Well, I would say it's slightly differently. It'd be great if we could come up with algorithms that could need less computation. There's a real need for that. This growing a factor of 10 every year for training, or factors of 100 every 2 years, is just pretty unaffordable. I think the GPT-3 model, my understanding that I mentioned, took months to train, even on 8,000 GPUs. So it's a huge computation. It's one of the biggest computations that I know about. So the excitement is, by making it tremendously bigger, it gets so accurate that it's becoming even more useful. So that's the temptation, but it would be fantastic if there were less expensive ways to train. Right now, what we're doing, everybody's working on machine learning now. Right now, what we're doing in the hardware space is trying to find more cost-efficient ways to scale up to really big designs. But boy, if we had better algorithms, that would be fantastic. I'd be surprised if there's some algorithm that could just get all the work done on your desktop CPU. That'd be an amazing breakthrough. I think you're going to need more hardware, but it'd be great if it wasn't as expensive as it is today.
So the last question we are probably able to handle in this session. What do you think about wafer scale processors? Or in other words, does it make sense to just combine more and more units into one piece of silicon? I think you addressed this briefly. But
yeah, I'll try and be quick. Wafer scale is where instead of taking the wafer and dividing it up into pieces, which we call chips or dies, is the normal way, and then putting them into packages, reassembling them. The wafer is just make the whole wafer be the computer. And Cerebras is doing that. That's the startup company. It's a very creative, exciting way. It's not clear yet whether it's cost effective. It's certainly revolutionary. If it proves to be cost effective, then they'll have a head start because it's an idea that has been around for decades that many people have gone out of business trying to do. If Cerebras makes it work, it'd be a very exciting, innovative way of building computers. I don't think it's a necessary way, but it could be a big advantage if they can make it work.
Thank you very much, David, for your presentation and for the Q&A session. We really appreciate it. And we're looking, of course, forward to seeing you in person again in Heidelberg next year, talking about the latest progress in this area. If you have time and interest, you can join our VR space and meet some of our participants and discuss with them or some other part of the program. For the time being, thank you very much for joining us, and it was a great talk.
Well,
to the audience,
I just wanted to thank you for all your work on the Heidelberg Forum. It's been fantastic. So we'll miss you when you're gone.
There will be a successor, and the show will go on, no problem. The next session will start at 20 hours CEST, and stay tuned. It will be Alan Kay talking about the process of innovation and the problem solving. Again, thank you, everybody.